two machines launched in 1977 are now farther from Earth than anything humanity has ever built. 13 billion miles into the void, Voyager 1 and 2 crossed a boundary we thought would be silent. Instead, they detected something moving, something pushing back against our solar system. A wall of plasma, denser than anything predicted, particles racing at impossible speeds, and a sound, a hum that should not exist in the vacuum of space. If you're ready to explore what lies at the edge of everything we know, hit that like button and subscribe. What Voyager found changes everything. Let's begin. The mission planners gave Voyager 1 a simple task: fly past Jupiter, photograph Saturn, then drift into the dark. Nobody expected it to last 5 years, let alone 45. The spacecraft carried a gold record with sounds from Earth, messages in 55 languages, and images of human life. A time capsule meant for aliens who might find it millions of years from now. But the engineers built something more durable than they realized. Both Voyagers launched in 1977, taking advantage of a planetary alignment that happens once every 175 years. This gravitational assist allowed them to visit multiple worlds without carrying enough fuel to reach even one. Jupiter's gravity slung Voyager 1 toward Saturn. Saturn's gravity pushed it upward, out of the flat plane where planets orbit. Voyager 2 took a different path, visiting Uranus and Neptune before heading downward into space. By the early 2000s, both craft had left the planets behind. They were entering a region scientists called the termination shock. This is where the solar wind, a stream of charged particles flowing from our star at 1 million miles per hour, begins to slow down. Think of it like a river meeting an ocean. The current keeps pushing, but something ahead resists. The first strange reading came from Voyager 1 in 2004. Scientists expected the solar wind to weaken gradually. Instead, the instruments showed wild fluctuations. The wind speed dropped, then surged, then dropped again. Over months, the pattern repeated. Something out there was pushing back in waves. Then the cosmic ray detectors started acting up. Cosmic rays are high-energy particles from outside our solar system, from exploding stars and colliding galaxies. They stream through space at nearly light speed. Earth's magnetic field and the solar wind normally shield us from most of them. But as Voyager traveled farther, scientists expected cosmic ray levels to rise smoothly. They did not. The levels spiked, then they fell, then they spiked higher. The data made no sense. It was like watching a wall appear and disappear. Some invisible barrier was blocking these particles, then letting them through, then blocking them again. The engineers checked the instruments. Everything functioned normally. The readings were real. Mission scientists proposed a new model. Maybe the edge of our solar system was not a clean line. Maybe it rippled. Maybe it breathed. The solar wind flows outward, but it changes strength depending on activity on the solar surface. When our star is active, the wind blows harder, pushing the boundary farther out. When it is quiet, the wind weakens, and the boundary contracts. Voyager was flying through a zone that moved, but that explanation did not account for everything. The magnetic field readings showed something unexpected. The field lines, which should have started pointing in new directions as Voyager left the solar magnetic influence, stayed mostly the same. It was like walking through a doorway and finding the same room on the other side. In 2009, Voyager 1 entered a new region entirely. The solar wind slowed to zero, not gradually, not over weeks. Within a few days, the outward flow stopped. The spacecraft now drifted in a zone where particles moved sideways, parallel to the boundary. Scientists called it the magnetic highway, a corridor where solar and interstellar particles could flow in both directions. This region was never predicted. Every model of the heliosphere, the bubble of solar influence around our star system, showed a simple boundary: inside, solar wind; outside, interstellar space. But Voyager found a third zone, a buffer, a place where two cosmic environments mixed and fought for dominance. What lay beyond this highway, no one knew, but Voyager kept transmitting, and the data kept getting stranger. Temperature in space is a strange concept. There is no air to feel hot or cold, but particles have temperature based on how fast they move. Voyager's instruments measured this by detecting particle speed and energy. In the solar wind region, temperatures reached around 100,000 degrees, hot enough to vaporize any material instantly. Yet the plasma was so thin that a human would freeze to death in seconds. Heat requires density, and space has almost none. As Voyager 1 moved into the magnetic highway, scientists expected temperatures to drop. The solar wind was slowing. After all, slower particles mean lower temperature. Basic physics. But the readings showed the opposite. Temperatures climbed. In some measurements, they jumped to over 250,000 degrees, higher than anything recorded closer to Earth. The data caused arguments among the mission team. Some thought the instruments were failing. 40 years in space, bombarded by radiation, subjected to temperature swings, from negative 270 degrees to boiling, the sensors had every reason to malfunction. But cross-checking with other instruments showed consistency. The readings were accurate. Then Voyager 2, traveling through a different region billions of miles away, reported the same thing. Higher temperatures at the boundary. This eliminated the instrument failure theory. Both spacecraft, with different trajectories and separate systems, detected the same phenomenon. The explanation involved physics most people never consider. When the solar wind collides with the interstellar medium, the particles do not just stop. They compress, they pile up. Imagine cars on a highway, hitting sudden traffic. The kinetic energy has to go somewhere. It converts to heat. The boundary region becomes a zone of extreme compression, where particles slam into each other millions of times per second. But there was another factor, magnetic reconnection. This happens when magnetic field lines from different sources cross and snap, releasing enormous energy. Think of it like rubber bands, stretched tight, then suddenly breaking. The energy does not disappear. It heats the surrounding plasma to extreme temperatures. At the edge of our solar system, field lines from the solar magnetic field meet field lines from interstellar space. They tangle, they break, they release energy constantly. Voyager detected bursts of this reconnection. The temperature would spike over hours, then settle, then spike again. Each burst was like a small explosion, though spread across millions of miles. These events accelerated particles to incredible speeds, sending them racing in all directions. The temperature readings also revealed something about the medium itself. Interstellar space is not uniform, it has clouds. Some regions are dense with hydrogen gas, others are nearly empty. Voyager appeared to be approaching a denser region, which would naturally increase particle collisions and temperature. Scientists calculated that the local interstellar cloud, the region of space our solar system currently moves through, has a temperature of around 13,000 degrees, far cooler than the boundary zone, but still hot by human standards. This cloud is part of a larger structure called the local bubble, a cavity blown out by ancient supernova explosions millions of years ago. We live inside the bubble's edge. The temperature mystery connected to another puzzle. If the boundary was this hot, why did the solar wind stop so abruptly? Hot plasma should push back harder. It should create more resistance. Yet Voyager found a zone where the wind just froze in place, unable to push farther. Something was applying equal pressure from the outside. That something was interstellar plasma, the medium between stars. For decades, scientists knew it existed but had no direct measurements. Theory suggested it was thin, cold, and mostly invisible. Voyager proved otherwise. It was hot, it was dense enough to stop the solar wind, and it carried its own magnetic field, one that fought against our solar system's influence. The The spacecraft was approaching the true boundary, and the temperature data hinted that crossing it would be violent. The heliosphere is the name for our solar system's protective bubble. It extends far beyond the planets, shaped by the solar wind pushing outward against interstellar pressure. Scientists thought they understood its shape. Models showed a smooth sphere, maybe stretched into a teardrop by our movement through the galaxy. Observations from distant stars suggested every stellar system had one. Ours should be no different. Voyager proved every model wrong. The first hint came from particle measurements. If the heliosphere was symmetric, both Voyagers should have encountered similar conditions at similar distances. They did not. Voyager 1 crossed the termination shock, the first major boundary, at 94 astronomical units from Earth. 1 astronomical unit equals the distance from Earth to our star, about 93 million miles. Voyager 2 crossed at 84 astronomical units, 10 astronomical units closer. That difference represents nearly 1 billion miles. A massive gap that no model predicted. The reason involved the interstellar magnetic field. Our solar system moves through the galaxy at 43,000 miles per hour. We orbit the galactic center, taking 230 million years to complete one circuit. As we move, the interstellar medium does not part smoothly. It pushes against the heliosphere like wind against a balloon. This creates asymmetry, but the level of asymmetry shocked researchers. The heliosphere's nose, the side facing our direction of travel, gets compressed. The tail, the opposite side, stretches out. Voyager 1 traveled through the nose region. Voyager 2 traveled through the side, closer to the tail. The difference in boundary location revealed that the heliosphere is not round. It is squashed, maybe even lopsided. New models incorporated this data. They showed a heliosphere shaped like a croissant with a flattened front and a stretched, possibly fragmented tail. Some simulations suggested the tail does not even exist as a single structure. Instead, it might break apart into multiple lobes, twisted by magnetic forces. Radio astronomers tried to observe the heliosphere from outside. They used distant sources, like pulsars, which emit regular radio pulses. By measuring how those pulses change as they pass through our solar system's edge, scientists hoped to map the boundary. The results were confusing. The boundary appeared to be in different places depending on the direction they looked. It moved, it shifted, it behaved nothing like a stable sphere. Voyager's data explained why. The heliosphere responds to the solar cycle. Every 11 years, our star's activity peaks and then fades. During high activity, the solar wind strengthens, pushing the boundary outward. During low activity, the wind weakens, and interstellar pressure pushes back, shrinking the bubble. The heliosphere breathes. But the breathing pattern is not simple. The solar magnetic field flips every 11 years. North becomes south, south becomes north. This flip sends shockwaves through the heliosphere, disrupting the boundary for months. Voyager detected these disruptions as sudden changes in particle density and magnetic field direction. The edge of our solar system is not stable. It is a war zone, where two environments constantly battle. The shape also affects cosmic ray entry. Cosmic rays do not penetrate the heliosphere evenly. They enter more easily through the nose, where the magnetic field is compressed and can create gaps. They enter less easily through the tail, where the magnetic field lines stretch and tangle, forming a better shield. This means Earth experiences varying cosmic ray levels depending on where the heliosphere boundary is at any given time. Scientists realized that if our protective bubble has this shape, it has been exposing Earth to more radiation during certain eras. When the solar cycle is weak and the heliosphere shrinks, cosmic rays flood in. These particles can affect cloud formation in our atmosphere. They can damage satellites. They may even influence mutation rates in living organisms over millions of years. Voyager's measurements forced a complete rethinking of how stars and their environments interact. Every star system, with a stellar wind, creates a heliosphere. But their shapes depend on countless factors: the star's strength, the density of surrounding space, the direction of travel, the local magnetic field. No two are alike. Our bubble is stranger than anyone imagined, and Voyager was about to pierce its outer wall. In August 2012, Voyager 1's instruments registered a sudden shift. The number of solar particles dropped by half in one day. This was not a gradual decline. This was a cliff. One moment, the detectors counted thousands of solar particles per second. The next, they counted hundreds. Something had changed. At the same time, galactic cosmic rays surged. These are particles from outside our solar system, accelerated by supernova remnants and other violent events across the galaxy. Voyager had been detecting a steady increase in cosmic rays for months as it approached the boundary, but on this day, they jumped 30% in hours. The science team debated what it meant. Had Voyager left the heliosphere? Was this the crossing? The boundary between solar and interstellar space? Not everyone agreed. The magnetic field measurements showed no change. Voyager was still detecting the solar magnetic field, the same orientation it had measured for years. If the spacecraft had truly left the solar bubble, the magnetic field should have rotated. It should have aligned with the interstellar field, which comes from a different direction entirely. For months, scientists argued. Some said Voyager had crossed. Others said it was still inside, just in a strange transition zone. The debate played out in scientific journals and press conferences. NASA hesitated to make an official announcement without certainty. Then in April 2013, something remarkable happened. A solar eruption sent a shockwave through space. These eruptions, called coronal mass ejections, blast billions of tons of plasma outward at millions of miles per hour. When they reach the heliosphere's edge, they shake the boundary like a gong. Voyager detected the vibration, but it came in the form of plasma oscillations. The plasma around the spacecraft began to vibrate at a specific frequency. By measuring that frequency, scientists could calculate plasma density. The denser the plasma, the higher the frequency. The frequency Voyager measured was 40 times higher than plasma inside the heliosphere. 40 times. This was not a small change. This was a different environment entirely. The spacecraft was surrounded by interstellar plasma. That confirmed it. Voyager 1 had crossed the heliopause, the official boundary between our solar system's influence and interstellar space. It had crossed in August 2012. The plasma measurement proved it. Humanity had sent a machine beyond the solar empire for the first time, but the magnetic field puzzle remained. Why had the field not rotated? Scientists proposed a new explanation. The interstellar magnetic field and the solar magnetic field happened to be aligned in the same direction in this region. By cosmic coincidence, they pointed the same way. This meant Voyager could not detect the change by field orientation alone. Only plasma density revealed the truth. Later measurements from Voyager 2, which crossed the heliopause in November 2018, showed a different story. When Voyager 2 crossed, the magnetic field did rotate. It shifted direction over days, aligning with the interstellar field. This confirmed that Voyager 1's crossing was unusual. The two craft exited through different parts of the boundary with different local conditions. The crossing itself happened over a region about 3 astronomical units thick, not a sharp line, but a turbulent zone where solar and interstellar influences mixed. Particles from both sides swirled together, magnetic field lines tangled, energy released in bursts. Voyager spent weeks in this transition, instruments recording every fluctuation. What surprised scientists most was how active the boundary was. They expected a calm interface. Instead, they found chaos. Waves propagated through the plasma constantly. Particles accelerated to high energies. The boundary rippled and shifted by billions of miles depending on solar activity. This had implications for other star systems. If our heliosphere's edge is this dynamic, then every stellar boundary is probably similar. A churning, energetic interface where two cosmic environments collide. Not a wall, but a battlefield. Voyager 1 now travels through the local interstellar medium, the material between stars in our region of the galaxy. It has entered a realm no human-made object has ever explored, and its instruments continue to transmit data, one bit at a time, from the other side. Cosmic rays are the universe's artillery. They are atomic nuclei, stripped of electrons, accelerated to nearly light speed by shock waves from dying stars. When they strike Earth's atmosphere, they shatter into cascades of secondary particles. A single cosmic ray can trigger a shower of millions of particles reaching the ground. They have enough energy to flip bits in computer memory, damage DNA, and create flashes of light in astronauts' eyes. The heliosphere shields us from most of them. The solar wind and its magnetic field deflect lower energy cosmic rays, bending their paths away from the inner solar system. Only the most energetic ones punch through. This protection is why life thrives on Earth. Without it, surface radiation levels would be far higher. Evolution might have taken a different path, or stalled entirely. Voyager's mission included cosmic ray detectors. These instruments count the number of particles hitting the spacecraft and measure their energy. As Voyager traveled outward, the count slowly increased. Closer to Earth, it detected around 100 million cosmic rays per square meter per second. At the termination shock, that number doubled. Scientists predicted it would keep rising until Voyager left the heliosphere entirely. But the data did not follow predictions. The cosmic ray count rose, then plateaued, then rose again. It behaved like a staircase instead of a ramp. Each step corresponded to Voyager entering a new region with different shielding properties. The termination shock was one step. The magnetic highway was another. The heliopause was the final step. After crossing the heliopause, cosmic ray levels jumped to around 900 million particles per square meter per second, nearly 9 times higher than near Earth. This is the background radiation level of interstellar space. Everything beyond the heliosphere experiences this bombardment constantly. The energy spectrum of the cosmic rays also changed. Inside the heliosphere, Voyager detected mostly lower energy particles. Outside, it detected the full range, including ultra-high energy cosmic rays with energies exceeding billions of electron volts. These particles carry so much energy that a single one hitting a human cell could cause catastrophic damage. Scientists analyzed where these cosmic rays come from. Most originate in supernova remnants within our galaxy. When a massive star explodes, it creates a shockwave that expands for thousands of years. This shockwave accelerates particles to enormous speeds. The Milky Way galaxy contains around 300 billion stars. Hundreds of them explode every century. Each explosion seeds the galaxy with cosmic rays. Some cosmic rays come from even farther away. Extragalactic cosmic rays originate in other galaxies, possibly from supermassive black holes or colliding galaxy clusters. These are the rarest and most energetic. Voyager detected a handful, confirming they can reach our local interstellar region. The cosmic ray data revealed something important about the heliosphere's shape. Cosmic rays do not penetrate evenly. They enter more easily through regions where the magnetic field is weak or tangled. The nose of the heliosphere, compressed by our motion through space, has a stronger magnetic field and blocks more cosmic rays. The tail, stretched and possibly fragmented, offers less protection. This means Earth's cosmic ray exposure varies over time. When the heliosphere shrinks during solar minimum, more cosmic rays reach the inner solar system. When it expands during solar maximum, fewer get through. Historical records show correlations between solar cycles and cosmic ray levels measured on Earth. Some scientists propose that cosmic ray variations affect Earth's climate. The theory suggests that cosmic rays seed cloud formation by ionizing the atmosphere. More cosmic rays mean more clouds. More clouds mean cooler temperatures. This remains controversial. But Voyager's data provides the baseline measurements needed to test such ideas. Voyager also detected something unexpected. The cosmic ray count fluctuated over days and weeks, even in interstellar space. This means the local interstellar medium is not uniform. There are clouds and voids. Some regions have higher particle density, which blocks cosmic rays. Others are emptier, allowing more through. Voyager is flying through this structure, encountering different environments as it goes. The spacecraft now travels through a shooting gallery. Cosmic rays strike it constantly. Each hit deposits a tiny amount of energy, slowly degrading the instruments and electronics. But the systems are robust. They were designed to survive Jupiter's radiation belts, which are far more intense. In interstellar space, Voyager endures. Light takes over 21 hours to travel from Voyager 1 to Earth. That means every command sent to the spacecraft has a 42-hour round-trip delay. Send an instruction. Wait 21 hours for it to arrive. Wait 21 more to confirm it worked. This communication lag makes every decision critical. There are no quick fixes, no emergency interventions. If something goes wrong, Voyager must handle it alone for almost 2 days before ground controllers even know. The spacecraft transmits at 23 watts. That is less power than a refrigerator light bulb. This faint signal travels across 13 billion miles, spreading out in all directions. By the time it reaches Earth, the signal is one of the weakest ever detected by human technology. Only the massive dish antennas of the Deep Space Network can pick it up. Those antennas are scattered across the planet. Goldstone in California, Madrid in Spain, Canberra in Australia. Together, they provide continuous coverage as Earth rotates. When one antenna loses sight of Voyager as it drops below the horizon, another picks up the signal on the opposite side of the planet. The system never sleeps, but time is running out. Voyager's power comes from radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. At launch, they produced 470 watts. Now, they produce around 250. The output drops by 4 watts every year as the plutonium decays. There is no way to stop it, no way to recharge. Mission engineers face hard choices. Every instrument on Voyager draws power. The cosmic ray detector, the plasma sensor, the magnetometer, the radio transmitter, the heaters that prevent critical systems from freezing. Together, they need more power than the generators currently produce. So the team shuts down instruments one by one. In 2007, they turned off the tape recorder used to store data. In 2008, the planetary radio astronomy instrument went dark. In 2020, the ultraviolet spectrometer shut off. Each loss diminishes Voyager's ability to study its environment, but extends the mission by years. The engineers have a plan. Keep the most critical instruments running as long as possible. Prioritize the plasma sensor and magnetometer. These tell scientists where Voyager is and what surrounds it. The cosmic ray detector can stay on too. As it uses minimal power, everything else is negotiable. By 2025, Voyager will no longer have enough power to run heaters. The spacecraft will start freezing. Critical components will fail as temperatures drop below their operating limits. But engineers think some systems might survive longer than expected. Voyager has already endured colder temperatures than designed for. Maybe it can go colder still. The absolute deadline comes around 2035. By then, the generators will produce too little electricity to power any instruments. Voyager will go silent. Its transmitter will die. Ground controllers will send commands into the void and receive nothing back. The spacecraft will continue flying, but humanity will lose contact forever. Even after it goes silent, Voyager will keep moving. It travels at 38,000 miles per hour relative to our star. Nothing will slow it down. No air resistance in the vacuum of space. No friction. It will coast for millions of years. eventually leaving the local interstellar cloud and entering whatever lies beyond. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. It will cross that distance silently, its golden record still intact, its instruments frozen and dark. If anything finds it, they will see a relic from a species that reached beyond its world and touched the stars. But before the silence, Voyager still transmits. Every day, data streams back to Earth at 160 bits per second, slower than the earliest dial-up internet connections from the 1980s. But it is enough. Scientists receive measurements of magnetic fields, plasma density, cosmic ray counts, and temperatures. Each data packet offers a glimpse of an environment no human has seen. The mission team treasures every transmission. They know each one might be the last. Hardware can fail without warning. A cosmic ray could strike a critical component. A power surge could fry the transmitter. The fact that Voyager still functions after 45 years is a miracle of engineering, and the spacecraft has more to show us before it falls silent. Plasma is the fourth state of matter. Solid, liquid, gas, plasma. Most people never encounter it on Earth, except in lightning bolts or fluorescent lights. But in space, plasma dominates. Stars are made of plasma. The solar wind is plasma. The interstellar medium is plasma. Over 99% of the visible universe exists in this state. Plasma forms when gas gets so hot that electrons rip away from atoms. What remains are charged particles, ions, and electrons, moving independently. These charges interact with magnetic fields in ways neutral gas cannot. They spiral around field lines. They create electric currents. They generate waves that propagate across light years. Voyager's plasma sensor measures the density and speed of charged particles around the spacecraft. It does this by detecting how particles flow into a detector cup and how much energy they carry. The instrument is simple but effective. As Voyager crossed the heliopause, the plasma sensor detected a sudden change. Density jumped from around 0.003 particles per cubic centimeter to 0.13 particles per cubic centimeter. That is over 40 times higher. This shift confirmed that Voyager had entered the interstellar medium, where plasma is denser than inside the heliosphere. But density is only part of the story. Temperature matters too, and the temperature measurements confused everyone. Inside the heliosphere, plasma temperature varied, but averaged around 100,000 degrees. Outside, it should have been cooler. Interstellar space is colder, right? Wrong. The plasma Voyager detected in interstellar space had temperatures around 50,000 degrees, cooler than the boundary region, but still far hotter than theoretical predictions suggested. Scientists expected temperatures closer to 10,000 degrees. The discrepancy meant something was heating the interstellar medium. One explanation involved shock waves. Our solar system moves through the galaxy, and as it does, it compresses the interstellar medium ahead of it. This compression heats the plasma. Think of it like air in a bicycle pump. Compress it, and it warms up. The same principle applies on cosmic scales. Another heating source is magnetic reconnection. Field lines from different regions cross, snap, and release energy. This happens constantly throughout the galaxy. Each reconnection event heats the surrounding plasma. Over time, these countless small heating events keep the interstellar medium warmer than it would otherwise be. Supernova remnants also contribute. When massive stars explode, they inject enormous amounts of energy into the surrounding space. This energy propagates outward as a shock wave, heating everything it encounters. Our local region of space sits inside a structure called the local bubble, a cavity blown out by multiple supernova explosions millions of years ago. The interior is hotter than the denser regions outside it. Voyager's plasma measurements also revealed oscillations. The plasma density varied slightly over hours and days. These oscillations are waves moving through the medium. Some come from solar eruptions that reach beyond the heliopause, disturbing the interstellar plasma. Others come from the galaxy itself, from distant events propagating through space. By measuring the frequency of these waves, scientists can determine how fast they travel, and the speed depends on plasma density and magnetic field strength. This makes plasma waves a diagnostic tool. They reveal the properties of the medium even when direct measurements are difficult. One particularly interesting measurement came in 2012. A solar eruption sent a shock wave through the heliopause, and Voyager detected the resulting plasma oscillation. The wave had a frequency of 2.6 kHz, far too low for human ears to hear, but computers can shift it into audible range. When mission scientists did this, they heard a rising tone, like a whistle. The heliosphere was ringing like a bell. This sound revealed the plasma density with precision. By analyzing the frequency, they calculated exactly how dense the interstellar plasma was in that region. It matched the direct measurements from the plasma sensor, confirming both instruments worked correctly. The plasma data also showed that the interstellar medium is not static. It flows. Our solar system moves through it, but the medium itself moves too, carried by galactic rotation and local currents. Voyager measures this flow by detecting how fast plasma moves relative to the spacecraft. The measurements show a complex pattern of motion, with the medium flowing in directions that vary over time. Understanding this flow matters for long-term predictions. As our solar system continues its orbit around the galaxy, it will enter different regions of the interstellar medium. Some will be denser, some will be thinner. The heliosphere will respond by shrinking or expanding. Earth's cosmic ray exposure will change accordingly. Voyager provides the baseline data for these predictions. The bow shock was supposed to be there. Every model predicted it. When our solar system moves through the interstellar medium, it should create a shock wave ahead of itself, just like a boat moving through water creates a bow wave. The heliosphere plows through space at 43,000 miles per hour. The interstellar medium should pile up in front of it, compressing and heating. That compression should form a distinct shock front, a region where the medium suddenly changes density and temperature. Observations of other stars showed bow shocks. Infrared telescopes captured images of stars surrounded by glowing arcs of heated gas, clear evidence of shock fronts. Our solar system should have one too. Scientists calculated where it would be, about 230 astronomical units from our star, roughly twice the distance where Voyager crossed the heliopause. But Voyager detected nothing. No sudden jump in pressure, no temperature spike, no density change that indicated a shock front. The spacecraft flew through the region where the bow shock should exist and measured only gradual variations. At first, scientists thought Voyager simply missed it. Space is vast. The bow shock might curve around the heliosphere, and Voyager's trajectory could have passed through a gap. But as time went on and the data accumulated, a different conclusion emerged. The bow shock does not exist, at least not in the way models predicted. The reason involves the local interstellar medium. Our solar system currently travels through a relatively empty region called the local fluff. This is a cloud of gas with low density, around 0.3 atoms per cubic centimeter. That is 100 times less dense than the densest interstellar clouds. For a bow shock to form, the medium must be dense enough to pile up and compress. If the medium is too thin, the solar system just passes through it without creating a shock. It is like the difference between running through water versus running through air. Water resists and creates waves. Air barely resists at all. The local fluff is borderline, dense enough to create some compression, but not dense enough for a sharp shock front. Instead, Voyager detected what scientists now call a bow wave, a gentle increase in density and pressure over a vast region spread across billions of miles rather than concentrated in a narrow boundary. This discovery forced a revision of heliosphere models. The solar system's interaction with its environment depends heavily on local conditions. When we pass through denser regions of the galaxy, a bow shock will form. When we pass through thinner regions, it will not. We happen to be in a thin region now, but this will change. Our solar system orbits the galaxy, and over millions of years, it encounters different environments. Around 10,000 years ago, we exited a denser cloud called the local interstellar cloud. The heliosphere was smaller then, and a bow shock probably existed. We entered the local fluff only recently in cosmic terms. In the future, we will exit the local fluff and enter another denser region. When that happens, the heliosphere will shrink. The bow shock will reappear. Cosmic ray levels reaching Earth will increase. This transition might happen in the next few tens of thousands of years, though exact timing is uncertain. Scientists now understand that the heliosphere is not a fixed structure. It is dynamic, constantly adjusting to the surrounding medium. The boundary moves, the shape changes, the bow shock comes and goes. Voyager happened to fly through during a time when the shock is absent or weak. Other star systems experience the same variability. A star moving through a dense nebula will have a compressed heliosphere with a strong bow shock. A star in an empty void will have an expanded heliosphere with no shock at all. The environment matters as much as the star itself. This realization changed how scientists interpret observations of other stellar systems. When telescopes detect bow shocks around distant stars, it means those stars are moving through dense regions. When no shock is visible, it does not mean the models are wrong. It means the star is in a low-density environment. Voyager's non-detection of a bow shock became one of the mission's most important findings, not because it found something, but because it confirmed the absence of something. And in science, sometimes what is not there tells you as much as what is. The spacecraft continues flying. Where the bow shock should have been, space extends unbroken. And Voyager keeps measuring. Pressure is not a concept most people associate with the vacuum of space. But space is not truly empty. It contains particles, even if only a few per cubic centimeter. Those particles move, they collide, and collectively, they exert pressure. The solar wind creates pressure. Millions of tons of plasma flow outward from our star every second. This wind pushes against anything in its path. It inflates the heliosphere like air inflates a balloon. The pressure is tiny by Earth standards, around a billionth of atmospheric pressure at sea level. But over vast distances, it matters. The interstellar medium also creates pressure. Particles in the space between stars move at different speeds, in different directions, creating a kind of gas pressure. This presses inward on the heliosphere from all sides. The boundary between solar and interstellar space is where these two pressures balance, where the outward push of the solar wind equals the inward push of the interstellar medium. Voyager measured both. Inside the heliosphere, instruments detected the ram pressure of the solar wind particles striking the spacecraft. Outside, they measured the thermal pressure of the interstellar plasma. The transition happened over days as Voyager crossed the heliopause. Pressure from the solar wind dropped to nearly zero. Pressure from the interstellar medium increased to around 3 × 10 to the negative 13 pascals. That number means nothing to most people. To put it in perspective, atmospheric pressure at Earth's surface is around 100,000 pascals. The interstellar medium has a trillionth of that. But in the context of space, it is significant. It is enough pressure to compress the heliosphere, enough to push the boundary inward when the solar wind weakens. Scientists had debated for decades whether interstellar pressure was uniform or variable. Voyager's data answered this. The pressure varies. Some regions of the local interstellar medium are denser and exert more pressure. Others are thinner and exert less. As our solar system moves through these regions, the heliosphere expands and contracts in response. The pressure imbalance also explains the heliosphere's asymmetric shape. The nose, facing our direction of travel through the galaxy, encounters higher pressure because we are moving into the medium. The tail, facing backward, encounters lower pressure because we are moving away from it. This creates a teardrop shape, compressed in front and stretched behind. But there is more complexity. Magnetic fields add another form of pressure. Magnetic pressure pushes outward when field lines are compressed. The solar magnetic field and the interstellar magnetic field both contribute. Where field lines pile up, pressure increases. Where they spread out, pressure decreases. At the heliopause, these magnetic pressures fight. The solar field tries to push outward. The interstellar field tries to push inward. Neither wins completely. Instead, they create a turbulent boundary layer where the fields tangle and reconnect, releasing energy. Voyager's magnetometer detected this turbulence. The magnetic field strength fluctuated wildly near the heliopause, varying by factors of 2 or 3 over hours. These fluctuations are magnetic pressure waves, ripples propagating through the boundary layer. They shake the entire structure, causing it to ripple and pulse. The pressure measurements also revealed how the boundary responds to solar activity. When a coronal mass ejection reaches the heliopause, it temporarily increases the outward pressure. The boundary bulges outward by billions of miles. Then, as the eruption dissipates, the boundary relaxes back. These bulges propagate around the heliosphere like ripples on a pond, taking months to spread and fade. Interstellar pressure varies on longer timescales too. As our solar system moves through the galaxy, it encounters regions with different densities. A denser region exerts more pressure, compressing the heliosphere. A thinner region exerts less, allowing it to expand. This happens over thousands of years, timescales far too long for Voyager to measure directly. But by combining Voyager's data with observations of the interstellar medium from Earth-based telescopes, scientists can predict future changes. Models show that in around 10,000 years, our solar system will enter a denser cloud. The heliosphere will shrink significantly. Cosmic ray levels will increase. Earth's radiation environment will change. Pressure from outside, pressure from inside. The heliosphere exists in a constant tug-of-war. Voyager stands at the boundary, measuring the balance, and the balance keeps shifting. Magnetic fields are invisible. We cannot see them or feel them directly, but they control the structure of space. They guide charged particles along field lines. They store energy. They create pressure. And in the interstellar medium, they determine how matter moves. Earth has a magnetic field generated deep in its core by the motion of molten iron. This field extends into space, creating a protective bubble called the magnetosphere. Solar wind particles cannot easily cross magnetic field lines, so Earth's field deflects them, protecting the atmosphere from erosion. Our star has a magnetic field too, far stronger than Earth's. It extends throughout the solar system, carried by the solar wind. The field lines spiral outward like water from a rotating sprinkler, twisted by the rotation of the star itself. This is the interplanetary magnetic field, and it dominates the heliosphere's interior. The galaxy also has a magnetic field. It threads through the space between stars, aligned roughly with the galactic spiral arms. This field is weak, around a millionth the strength of Earth's field. But over light-year distances, it shapes clouds of gas and guides cosmic rays. Voyager's magnetometer measures field strength and direction. Inside the heliosphere, it detected the interplanetary magnetic field. The strength varied but averaged around 0.1 nanoteslas. The direction spiraled as expected, tracing the twisted geometry of the solar wind. As Voyager approached the heliopause, scientists predicted the field would change direction. The interplanetary field points in one direction based on the solar magnetic configuration. The interstellar field points in a different direction based on galactic structure. Crossing the boundary should produce a clear rotation from one orientation to the other. Voyager 1 detected no such rotation. The field direction stayed the same across the heliopause crossing. This baffled researchers for months. How could Voyager leave the heliosphere without the field changing? The answer came from plasma measurements, and later from Voyager 2. The interstellar magnetic field in Voyager 1's region happened to be aligned in the same direction as the interplanetary field. By pure chance, the two fields pointed the same way. So, even though Voyager crossed into interstellar space, the magnetometer saw no rotation. Voyager 2 crossed in a different region where the fields were not aligned. When it crossed the heliopause, the magnetometer detected a clear rotation over several days. The field direction shifted by about 45 degrees, gradually aligning with the interstellar field. This confirmed that Voyager 2 had exited the solar magnetic influence and entered the galactic field. The measurements also revealed that the boundary is not magnetically sharp. There is a transition zone where the two fields mix. Magnetic reconnection occurs constantly, snapping field lines from one side and connecting them to the other. This creates a layer of turbulence several astronomical units thick. Field strength varies significantly near the boundary. Inside the heliosphere, the interplanetary field measures around 0.1 nanoteslas. In the interstellar medium, the field measures around 0.4 nanoteslas, 4 times stronger. This surprised scientists. They expected the interstellar field to be weaker. A stronger interstellar field has implications. It affects how cosmic rays travel. Particles spiraling along field lines will follow the interstellar field's geometry, entering the heliosphere along certain directions more easily than others. This creates anisotropy, meaning cosmic rays do not come from all directions equally. The interstellar field's strength also affects the heliosphere's shape. Magnetic pressure from the interstellar field pushes against the heliosphere, contributing to its compression. In regions where the field is stronger, the compression is greater. In regions where the field is weaker, the heliosphere can expand more. Scientists realized that mapping the interstellar magnetic field requires more than Voyager's measurements. They need observations from multiple directions. Future missions could launch probes in different directions to sample the field in other regions. But for now, Voyager provides the only direct measurements. The magnetometer data also showed something subtle. The interstellar field is not uniform. It varies over time and distance. Voyager detected slow changes in field strength and direction as it flew through interstellar space. These variations reflect structure in the local interstellar medium. Clouds of gas have slightly different magnetic properties. Voids between clouds might have weaker fields. Understanding this structure matters for predicting how the heliosphere will change as our solar system moves through different regions. A stronger field will compress the heliosphere more. A weaker field will allow it to expand, and the field direction determines which cosmic rays can most easily reach Earth. Voyager keeps measuring. The magnetometer still functions, and the interstellar magnetic field still holds secrets. Voyager 2 followed a different path than its twin. Launched 16 days before Voyager 1, it flew slower and took a longer route through the outer planets. While Voyager 1 shot upward out of the solar system's plane after passing Saturn, Voyager 2 continued onward to Uranus and Neptune, then headed downward into space. By the time both reached the edge, they were billions of miles apart. This separation proved critical. If only one spacecraft had crossed the heliopause, scientists would have data from only one location. They could not distinguish between local conditions and universal patterns. But with two crossings in different regions, comparisons became possible. Voyager 1 crossed at 122 astronomical units in August 2012. Voyager 2 crossed at 119 astronomical units in November 2018. 3 astronomical units closer. That difference, around 280 million miles, revealed how much the boundary varies by location. The crossing experiences differed in almost every way. Voyager 1 detected a gradual increase in cosmic rays. over months before the final jump. Voyager 2 detected a sharper transition, with cosmic ray levels jumping more abruptly. Voyager 1 saw no change in magnetic field direction. Voyager 2 saw a clear rotation. Temperature measurements also differed. Voyager 1 encountered extremely hot plasma near the boundary, with temperatures exceeding 250,000 degrees. Voyager 2 detected cooler plasma, around 100,000 degrees. This suggested the boundary has hot spots and cool spots, regions where reconnection heats the plasma more intensely. Plasma density showed similar variation. Voyager 1 measured an interstellar plasma density of around 0.13 particles per cubic centimeter. Voyager 2 measured 0.09 particles per cubic centimeter. Lower density means lower pressure, which partly explains why Voyager 2 crossed closer to our star. The boundary pushed inward in that region. Solar activity also played a role. When Voyager 1 crossed, the solar cycle was approaching maximum activity. Solar wind strength was relatively high, pushing the boundary outward. When Voyager 2 crossed, the solar cycle was declining toward minimum. Weaker solar wind meant the boundary had contracted, but the timing difference was 6 years. In those 6 years, the solar cycle completed half its period. The heliosphere breathed in and out. The boundary moved billions of miles inward. Voyager 2 happened to cross during that contraction, encountering the heliopause much closer than Voyager 1. This taught scientists that no two crossings will ever be identical. The boundary is not a fixed location. It responds to solar activity, interstellar pressure, and local magnetic field variations. Any spacecraft leaving the heliosphere will encounter unique conditions depending on where and when it crosses. The two Voyagers also detected different fine structure near the boundary. Voyager 1 spent about a month in the transition zone, with instruments showing mixed signals from solar and interstellar influences. Voyager 2 spent only a few days in transition. The boundary was sharper in that location, compressed by external factors. Scientists debated why. One theory suggested that Voyager 2 crossed through a region where the interstellar magnetic field was stronger, creating more compression and a thinner boundary layer. Another theory proposed that solar activity had created a temporary bulge in the boundary near Voyager 1, stretching the transition zone. Both spacecraft also detected different levels of turbulence. Voyager 1 measured wild fluctuations in magnetic field strength near the heliopause, with values changing by factors of 2 or 3 over hours. Voyager 2 measured more stable fields with smaller fluctuations. This implied that some regions of the boundary are more chaotic than others. Comparing the two crossings allowed scientists to separate universal features from local anomalies. Universal features, seen by both spacecraft, include the increase in cosmic rays, the increase in plasma density, and the change from solar to interstellar magnetic influence. Local anomalies include the exact distance of the crossing, the temperature of the boundary plasma, and the sharpness of the transition. This distinction matters for building accurate models. Models must account for variability. They cannot assume the heliosphere has a fixed shape or that the heliopause is uniform. Reality is messier. The boundary ripples. It shifts. It responds dynamically to forces from both sides. Future missions will need multiple spacecraft to map the heliosphere properly. 1 or 2 are not enough. Dozens might be needed to capture the full three-dimensional structure and its time evolution. Voyager gave us 2 points, but a sphere requires far more. For now, those 2 points are all humanity has, and they tell a story of a boundary far more complex than anyone imagined. Before Voyager, scientists made predictions. They used the best physics available. They ran computer simulations. They extrapolated from data gathered near Earth, and they were wrong about almost everything. They predicted the termination shock would be at 90 astronomical units. Voyager 1 found it at 94. Voyager 2 found it at 84. 10-unit discrepancy. Models did not account for the asymmetry caused by the interstellar magnetic field and our motion through the galaxy. They predicted cosmic ray levels would increase smoothly as Voyager traveled outward. Instead, the levels rose in steps with plateaus in between. The magnetic highway region, where cosmic rays could flow along field lines parallel to the boundary, was not in any model. No one expected it. They predicted the heliopause would be a thin boundary, maybe a few million miles thick. Voyager found a transition zone stretching across hundreds of millions of miles. The boundary is not a wall, it is a frontier, a region where two environments battle for dominance. They predicted the bow shock would exist at around 230 astronomical units, a clear shock wave formed by our motion through the interstellar medium. Voyager detected no bow shock. The local interstellar medium is too thin to create one. The models assumed average galactic density. Reality is far from average. They predicted temperatures in interstellar space would be cooler than inside the heliosphere. Voyager found the opposite near the boundary. Magnetic reconnection and compression create hot zones where plasma reaches extreme temperatures. The boundary is not calm, it is energetic. They predicted the magnetic field would rotate clearly when Voyager crossed into interstellar space. Voyager 1 detected no rotation. By cosmic coincidence, the solar and interstellar fields aligned. Voyager 2 detected the rotation 6 years later. One data point would have led to wrong conclusions. 2 revealed the truth. They predicted the heliosphere was roughly spherical, maybe elongated slightly by our motion. Models now show it is asymmetric, compressed in front, stretched behind, possibly fragmented in the tail. Shape matters. It affects how cosmic rays enter and where Earth is most exposed. They predicted the solar wind would dominate out to a predictable distance. But the distance changes by billions of miles depending on solar activity and interstellar conditions. The heliosphere breathes. It swells and shrinks over 11-year cycles and longer timescales. Every prediction that failed taught something valuable. Science advances not just when predictions are confirmed, but when they are overturned. Wrong predictions reveal gaps in understanding. They force new theories. They lead to better models. Voyager's data spawned a generation of new heliosphere research. Scientists went back to first principles. They incorporated magnetic reconnection into models. They added asymmetry. They included time dependence. They accounted for the local interstellar clouds' properties. The new models match Voyager's data far better. But even the new models are incomplete. They make assumptions about regions Voyager has not yet reached. They extrapolate from 2 data points when dozens are needed. They simplify physics to make calculations possible. Reality is always more complex than models. Future missions will test these new predictions. NASA has considered an interstellar probe, a spacecraft designed specifically to study the heliosphere and beyond. It would fly faster than Voyager, reaching the heliopause in 15 years instead of 40. It would carry more advanced instruments. It would target specific regions to answer questions Voyager raised but cannot fully resolve. Such a mission would also fly in a different direction, providing a third data point. With 3 widely separated measurements, scientists could begin to map the heliosphere's 3-dimensional structure. They could test whether the tail is truly fragmented. They could measure the bow wave in different directions. They could determine if the hot zones Voyager detected are common or rare. The challenge is funding and technology. Building a spacecraft that can survive for decades and transmit from interstellar distances requires resources and commitment. Voyager cost around $800 million in today's money. An interstellar probe would cost several billion. Governments must decide if the science justifies the expense. Meanwhile, Voyager continues to provide data. Every transmission corrects old assumptions and challenges new ones. The spacecraft is a flying laboratory, reporting from a place no human-made object has ever been. It does this with instruments designed in the 1960s and 70s, technology from before personal computers, before the internet, before modern smartphones. That obsolete technology is rewriting our understanding of the cosmos, one bit at a time, one surprise at a time, and every surprise makes the universe a little stranger. Humans tend to think of space as uniform. A vacuum is a vacuum, empty is empty, but Voyager proved otherwise. Space has structure, textures, boundaries. And even within interstellar space, conditions vary dramatically from place to place. The local interstellar cloud, where our solar system currently resides, is not a single homogeneous entity. It is a collection of filaments, knots, and voids. Some regions have higher hydrogen density, others are nearly empty. Temperature varies by tens of thousands of degrees across light years. Magnetic field strength changes by factors of 2 or 3. Voyager measures this structure as it flies. The spacecraft moves at about 38,000 miles per hour relative to our star, but only around 22,000 miles per hour relative to the local interstellar medium. This slower relative motion means Voyager takes years to traverse even small-scale structures in the cloud. So far, Voyager has detected several variations. Plasma density fluctuates slightly over months, sometimes 0.1 particles per cubic centimeter, sometimes 0.08. The changes are small but measurable. They indicate Voyager is flying through regions with different concentrations of gas. Magnetic field direction also shifts gradually. Over years, the field has rotated by a few degrees. This rotation is not random. It reflects the large-scale structure of the galactic magnetic field and how it drapes over the local interstellar cloud. The field lines curve and twist, following the flow of gas through the galaxy. Temperature measurements show a cooling trend. Near the heliopause, plasma temperatures were around 50,000 degrees. Farther out, temperatures have dropped to around 40,000 degrees. This suggests Voyager is moving away from the hot boundary region and into cooler interstellar space. But the cooling is not smooth. There are spikes, brief periods where temperature increases for days before dropping again. These spikes might be shock waves from distant sources propagating through the medium. Or they might be local heating events caused by magnetic reconnection or particle acceleration. Cosmic ray levels also vary. Most of the time, Voyager detects around 900 million cosmic rays per square meter per second. But occasionally, the count drops by 10 or 20% for weeks, then recovers. These dips suggest Voyager is passing through denser regions where cosmic rays are partially blocked. The structure Voyager measures is tiny compared to the galaxy. The local interstellar cloud is about 30 light-years across. Voyager has traveled less than 1% of 1 light-year into it. At current speed, crossing the entire cloud would take hundreds of thousands of years. But even within this small region, Voyager detects meaningful variation. Scientists compare Voyager's measurements to observations from Earth-based telescopes. Radio telescopes can detect emissions from hydrogen gas in the local cloud. Infrared telescopes can map dust. Ultraviolet telescopes can measure absorption lines from atoms between us and distant stars. Each technique provides a different view of the same region. Combining Voyager's in situ measurements with remote observations gives a more complete picture. The local cloud is elongated, stretched along the galactic plane. Its density is higher along certain lines of sight. Its temperature is not uniform. Magnetic fields trace complex patterns through it. This detailed mapping matters for understanding Earth's cosmic environment. As our solar system moves through the cloud, the heliosphere responds. When we enter denser regions, the heliosphere shrinks. When we enter thinner regions, it expands. These changes affect cosmic ray exposure on Earth. Some scientists propose that transitions between interstellar clouds can trigger ice ages. When our solar system exits one cloud and enters another, the heliosphere undergoes rapid changes. Cosmic ray levels spike. More cosmic rays reach Earth's atmosphere. Some theories suggest this increases cloud cover, reflecting more sunlight and cooling the planet. The evidence for this idea is debated. Ice ages have many causes: orbital variations, volcanic activity, ocean currents. Teasing out the contribution from cosmic rays is difficult, but Voyager's data provides the baseline measurements needed to test the hypothesis. Other implications involve radiation hazards for future space exploration. If humanity ever sends missions to nearby stars, those missions will traverse interstellar clouds, similar to the one Voyager measures now. Understanding the radiation environment is essential for protecting astronauts and electronics. Voyager is humanity's first probe into this environment. It is mapping the wilderness between stars, and the wilderness is not empty. It is filled with structure, energy, and processes we are only beginning to understand. Every instrument on Voyager was built in the 1970s. Engineers used vacuum tubes for some circuits. Transistors were hand-soldered. Computer memory was magnetic tape. Data storage was 8-track. The entire onboard computer has 68 kilobytes of memory. A modern smartphone has billions. Yet, this ancient technology still functions. 45 years in space, temperatures swinging from boiling to near absolute zero, radiation bombardment from cosmic rays, micrometeorite impacts, no maintenance, no repairs, and Voyager transmits. The spacecraft is a masterpiece of engineering simplicity. Redundancy built into every critical system, 2 radio transmitters in case one fails, 2 computers that can back each other up, instruments shielded by the spacecraft's body, power systems designed to degrade slowly and predictably. The key is the radioisotope thermoelectric generators. Plutonium-2, 38 decays with a half-life of 87.7 years. The decay produces heat. Thermocouples convert heat to electricity. No moving parts, no chemical reactions that can run out, just physics, steady and reliable. At launch, the generators produced 470 watts, enough to power all instruments, the transmitter, and the heaters that keep critical components warm. Now, they produce around 250 watts. By 2035, they will produce too little to run any instruments. Power failure is inevitable. Mission engineers manage this decline carefully. They calculate how much power each system needs. They prioritize. The transmitter is essential. Without it, Voyager cannot send data. The plasma sensor and magnetometer are next. They provide the most important scientific measurements. The cosmic ray detector uses minimal power, so it stays on. Everything else is negotiable. In 2012, engineers shut down heaters for some instruments. Those instruments got colder but kept working. In 2020, they shut down more instruments to conserve power. Each shutdown buys extra years of operation for the remaining systems. The spacecraft's attitude control is another challenge. Voyager must keep its antenna pointed at Earth. If the antenna drifts even a few degrees, the signal becomes too weak to detect. Thrusters make tiny adjustments, firing in short bursts to correct orientation. But the thrusters use fuel, and the fuel is running out. Engineers designed the system to last 30 years. It has lasted 45. The fuel supply is now so low that thruster firings must be minimized. Ground controllers calculate trajectories months in advance, planning the most efficient firing sequences. They have even switched to backup thrusters that have not been used since the 1980s. In 2017, one set of primary thrusters showed signs of clogging. Decades of residue buildup reduced their efficiency. Engineers activated thrusters that had been dormant for 37 years. They worked perfectly. This bought more time. Data transmission is equally challenging. Voyager transmits at 160 bits per second. That is slower than the slowest dial-up modem from the 1980s. It takes hours to send a single image. It takes days to transmit a full data dump from all instruments. The signal is incredibly weak. By the time it reaches Earth, The power is around a billionth of a watt. Only the 70-meter dish antennas of the Deep Space Network can detect it. These antennas are among the most sensitive receivers ever built. They can detect signals weaker than a snowflake landing. But even with these antennas, communication is precarious. Interference from Earth-based radio sources can drown out Voyager's signal. Solar weather can disrupt transmission. Equipment failures at the ground stations can cause data loss. Every transmission is precious. Engineers have developed tricks to maximize data return. They compress data before transmission. They prioritize the most important measurements. They schedule transmissions when Earth's ionosphere is most transparent. They coordinate with the 3 Deep Space Network stations around the world to ensure continuous coverage. The spacecraft's computer is another weak point. 68 kilobytes of memory was generous in the 1970s. Now, it is absurdly small. The computer cannot store large amounts of data. It cannot run complex programs. It operates on simple, pre-programmed routines. Yet this simplicity is an advantage. Simple systems are robust. They have fewer failure modes. They are easier to troubleshoot from billions of miles away. When something goes wrong, engineers can diagnose and fix it by sending new commands. The fixes are basic, but they work. Voyager will eventually fail. A critical component will break. The power will drop too low. The thrusters will run out of fuel. The antenna will drift off target. When that happens, contact will be lost forever. But until then, the spacecraft keeps flying, and every transmission is a small miracle. The Golden Record is Voyager's most famous cargo, a 12-inch gold-plated copper disc carrying sounds and images from Earth, greetings in 55 languages, music from different cultures, natural sounds like thunder, wind, and whales. 116 images showing human life, biology, and planetary science. Instructions for playing the record etched on the cover. The record is a time capsule, a message to whoever might find Voyager in the distant future, long after our civilization falls, long after our species evolves or goes extinct, long after our star expands into a red giant and consumes the inner planets. The record will endure. Gold does not corrode in the vacuum of space. There is no oxygen to oxidize it, no water to rust it, no atmosphere to weather it. Cosmic rays will gradually damage the molecular structure, but this takes billions of years. The record should remain playable for at least 1 billion years, possibly much longer. But the chances of anyone finding it are almost zero. Space is incomprehensibly vast. Voyager 1 is currently 13 billion miles from Earth. That sounds far. It is nothing. The nearest star system, Alpha Centauri, is 25 trillion miles away. Voyager will not come close to any star for tens of thousands of years. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. That is still 94 trillion miles. Far too distant for the star's gravity to capture the spacecraft. Voyager will sail past in the dark, unseen, and undetected. In around 300,000 years, Voyager will pass near another star, then another. Over millions of years, it will wander through the galaxy, drifting wherever gravity and chance take it. The odds of it encountering an alien civilization are essentially zero. Yet the record exists. Not because scientists expected it to be found, but because humans needed to send it. The act of creating the record mattered more than its destination. It was a statement, a declaration that we exist, that we create, that we reach beyond ourselves. Carl Sagan led the team that selected the record's content. They faced impossible choices. How do you represent all of humanity in 90 minutes of audio and 116 images? What music do you choose? What languages? What sounds define Earth? They included Beethoven's Fifth Symphony, Chuck Berry's Johnny B. Good, a pygmy girl's initiation song from Zaire, a Navajo night chant, Peruvian panpipes, Japanese shakuhachi, Bach's Brandenburg Concerto. Each piece represents a culture, a time, a way of humans expressing themselves through sound. The images include mathematical definitions so aliens can decode them, diagrams showing how to convert the digital information into pictures. Once decoded, the images show DNA structure, human anatomy, animals, landscapes, buildings, and technology. They show birth. They show family. They show the diversity of life on Earth. Critics pointed out the absurdity. Any species capable of intercepting Voyager would have technology far beyond ours. They would not need crude images and audio recordings to understand us. They would have better ways to learn about Earth. But the record was never really for aliens. It was for us. It forced humanity to think about how we would represent ourselves to the universe. It made us consider what is truly important: music, language, science, nature, community. These are what we chose to send into the void. The record also includes spoken greetings, 55 languages, from ancient Sumerian to modern Mandarin. Each speaker says something simple: greetings, peace, friendship. The messages are naive, perhaps, hopeful in the face of cosmic indifference. One greeting is in English, from then-President Jimmy Carter. It reads, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We are attempting to survive our time." That line resonates more every year. When Voyager launched, nuclear war threatened extinction. Climate change was barely acknowledged. Biodiversity loss was accelerating. We sent Voyager out, carrying a record of what we were, because we feared we might not last. Decades later, those threats remain. New ones have emerged, but Voyager still flies. The record still spins silently in its protective cover, and somewhere, billions of miles away, our message drifts through the dark. Whether anyone ever hears it does not matter. We sent it. That is enough. The heliopause is not a fixed line. It moves, it breathes, and its motion reveals something profound about the forces shaping our cosmic neighborhood. Solar activity follows an 11-year cycle. Every 11 years, the number of sunspots peaks. Solar flares erupt more frequently, and coronal mass ejections blast plasma into space. The solar wind strengthens during these peaks, pushing harder against the interstellar medium. The heliosphere expands. The heliopause moves outward by billions of miles. Then, activity declines. Sunspots disappear. The solar wind weakens. Interstellar pressure pushes back. The heliosphere shrinks. The heliopause contracts inward, sometimes by as much as 20 astronomical units. That is nearly 2 billion miles of movement. Voyager detected this breathing pattern. The spacecraft crossed the heliopause during solar maximum in 2012. If it had approached the boundary during solar minimum, it would have crossed years earlier. The boundary would have been closer. But the motion is not smooth. The heliopause does not expand and contract uniformly. It ripples. Waves propagate around it. When a coronal mass ejection reaches the boundary, it creates a temporary bulge that expands outward, then relaxes over months. These bulges travel around the heliosphere's surface like ripples on a pond. Voyager's instruments detected these ripples as the spacecraft approached the boundary. Particle counts would surge, suggesting the heliopause was nearby, then drop again, suggesting it had moved away. This back-and-forth pattern continued for years. The spacecraft was flying through a zone where the boundary oscillated back and forth faster than Voyager could cross it. Eventually, a strong solar eruption pushed the boundary outward enough that Voyager crossed and stayed in interstellar space. But even after crossing, the spacecraft detected effects from boundary motion. Plasma waves from solar eruptions propagated past the heliopause, disturbing the interstellar medium. The boundary's location affects the entire region around it. Scientists model this breathing using magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields. The equations are complex, requiring supercomputers to solve. Models show that the heliosphere can expand by 15 astronomical units during solar maximum and contract by the same amount during solar minimum. That is a 30 astronomical unit range of motion, nearly 3 billion miles. But the motion depends on interstellar conditions too. If the local interstellar medium becomes denser, it pushes harder, compressing the heliosphere more. If it becomes thinner, the heliosphere expands. Our solar system moves through the galaxy at 43,000 miles per hour, encountering different regions of the interstellar medium over time. Around 10,000 years ago, our solar system exited a denser cloud called the local interstellar cloud and entered the current region, the local fluff. When that transition happened, the heliosphere expanded significantly. Cosmic ray levels reaching Earth dropped. This might have affected climate, though the connections are unclear. In the future, we will exit the local fluff and enter another region. That transition will happen in the next 10 to 20,000 years. When it does, the heliosphere will shrink again. The heliopause will move inward. Cosmic ray levels will increase. Earth's radiation environment will change. These timescales are long by human standards but short in cosmic terms. Ice core data from Antarctica and Greenland preserves records of cosmic ray levels going back hundreds of thousands of years. Scientists can correlate those records with climate data, looking for patterns. Some studies suggest cosmic ray increases correspond to cooling periods. Others find no clear connection. Voyager's measurements provide the baseline for understanding these changes. By knowing the current state of the heliosphere and how it responds to solar activity, scientists can model what happens when interstellar conditions change. They can predict how much the heliosphere will shrink or expand. They can estimate cosmic ray levels Earth will experience. This matters for long-term planning. If cosmic rays increase significantly, it affects satellites. More radiation means more malfunctions. It affects astronauts. Higher radiation doses limit mission durations. It might even affect surface life, though Earth's atmosphere and magnetic field provide substantial protection. The heliosphere is our shield. Its size and strength determine how much radiation reaches us, and that size is not constant. It changes over years, decades, millennia. Voyager caught it at one moment in its breathing cycle, a snapshot of a dynamic system. The boundary keeps moving, and Voyager, now beyond it, keeps measuring the consequences. In 2012, an eruption on our star sent a shockwave through the heliosphere. The shockwave traveled outward at over 1 million miles per hour, crossing the heliopause and disturbing the interstellar plasma beyond. Voyager 1, already in interstellar space, detected the disturbance. But Voyager did not detect it as particles or magnetic fields. It detected sound, or rather, plasma oscillations that can be converted to sound. When the shockwave struck the interstellar plasma, it compressed the charged particles. This compression created a wave that propagated through the medium. The wave made the plasma vibrate at a specific frequency determined by its density and temperature. Voyager's plasma sensor measured these vibrations. The frequency was 2.6 kHz, far above the range of human hearing, but scientists could shift it down into audible frequencies. When they did, they heard a rising tone, a hum that increased in pitch as the wave passed through. It lasted for months before fading. This was not the first time Voyager detected plasma oscillations. In 2013, another solar eruption created similar disturbances. Again, Voyager measured the frequency and calculated plasma density from it. The results matched direct measurements from the plasma sensor, confirming the technique worked. But the remarkable thing was that these oscillations revealed something unexpected. The plasma was making sound all the time, not just during solar eruptions. There was a constant background hum, too faint for Voyager to detect initially, but present nonetheless. Scientists discovered this by analyzing Voyager's data more carefully. They looked for weak signals buried in noise. They found a faint oscillation around 30 Hz, far lower than the eruption-induced waves. This oscillation was persistent. It never stopped. What caused it? The interstellar medium is not still. It flows. Turbulence stirs it. Magnetic fields move through it. Shockwaves from distant sources propagate through it. All of this creates low-frequency oscillations that travel for light years. Voyager happened to be in a region where these background waves converged. The sound is real, though calling it sound stretches the definition. Sound on Earth is pressure waves in air. Molecules vibrate back and forth, transmitting energy. In space, plasma oscillations work similarly, but with charged particles instead of molecules. The physics is analogous. If a human could float in interstellar space and somehow survive, they would not hear this sound. The plasma is too thin. There are not enough particles to transmit pressure to an eardrum, but instruments can detect it, and those instruments reveal a universe far from silent. Scientists had always thought space was quiet. The famous tagline, "In space, no one can hear you scream," reflects this assumption. And it is true that space has no air to carry sound in the traditional sense. But it is not silent. It hums. It vibrates. It resonates with energy. The heliosphere itself creates sound. Solar eruptions ring the boundary like a bell. Plasma waves propagate through the solar wind. The termination shock, where the solar wind slows, creates turbulence that generates oscillations. All of these can be converted to audio if you have the right instruments. NASA released recordings of these sounds to the public. People could hear the heliosphere's vibrations, the hum of interstellar space, the rising tone of a shockwave passing through plasma. The recordings went viral. Millions of people listened to the sound of space for the first time. Some found it eerie, a low, droning hum that never ends. Others found it fascinating, proof that space is not the cold, dead void we imagined. It is active, alive with energy and motion. The plasma oscillations also serve a scientific purpose. By measuring their frequency, scientists can map plasma density across vast regions. Radio telescopes on Earth can detect similar oscillations from distant sources. Combined with Voyager's in situ measurements, this creates a three-dimensional picture of the local interstellar medium's structure. Future spacecraft could use this technique to navigate. Plasma oscillations change frequency as density changes. By monitoring these changes, a spacecraft could determine when it is entering denser or thinner regions, even without direct plasma sensors. Voyager keeps listening. The instruments record every oscillation, every fluctuation, and somewhere in that data, hidden in the noise, might be signals from events we do not yet understand. Explosions light years away, collisions between interstellar clouds, magnetic reconnection on galactic scales. Space is not silent. It never was. We just needed to reach far enough to hear it. The instruments aboard Voyager are analog, designed in an era before digital sensors dominated. They measure voltages, count particles, detect magnetic fields using simple coils of wire. No microprocessors in the sensors themselves. No advanced algorithms. Just physics, direct and unfiltered. This simplicity has kept them working for 45 years. Digital circuits can fail catastrophically. A single bit error can crash an entire system. Analog circuits degrade gradually. They give warning signs. Engineers can work around partial failures. The cosmic ray detector is essentially a solid-state telescope. Particles strike silicon detectors, creating electrical pulses. The size of the pulse indicates the particle's energy. The rate of pulses indicates particle flux. Simple concept, reliable execution. The magnetometer uses wire coils mounted on a boom extending away from the spacecraft. When a magnetic field passes through a coil, It induces a voltage. Measure the voltage. Calculate the field. 3 coils at different angles measure field strength and direction in 3 dimensions. The boom keeps the coils away from the spacecraft's own magnetic fields, which would contaminate readings. The plasma sensor is more complex. It contains 4 Faraday cups, detectors, that measure charged particles flowing into them. Each cup faces a different direction, allowing the instrument to determine not just particle density, but also flow direction and speed. The cups use voltage grids to filter particles by energy, separating fast from slow. But the plasma sensor on Voyager 1 has a problem. It stopped working properly in 1980. A circuit failed, limiting the instrument's range. For decades, it could only detect solar wind particles, not the denser interstellar plasma. Scientists thought Voyager 1 would cross the heliopause without its plasma sensor functioning. Then, in 2012, luck intervened. A solar eruption created oscillations in the interstellar plasma. These oscillations had a frequency that depended on plasma density. Voyager's other instruments detected the oscillations. Scientists calculated density from frequency. The plasma sensor was not needed. Voyager 2's plasma sensor still works. When it crossed the heliopause in 2018, it measured plasma density directly. The readings confirmed what scientists had calculated from Voyager 1's oscillation measurements. Both spacecraft agreed. Interstellar plasma density is around 0.1 particles per cubic centimeter. The instruments were never designed for interstellar space. Engineers built them to study Jupiter and Saturn. They expected the mission to last 5 years, maybe 10. Operating in interstellar space for decades was not in the design requirements, yet they function. Radiation damage is the biggest threat. Cosmic rays strike the spacecraft constantly. Each hit deposits energy. Over time, this degrades materials. Silicon detectors develop defects. Circuits develop leaks. Insulation breaks down. But the degradation is slow. The radiation environment in interstellar space is intense compared to Earth, but mild compared to Jupiter's radiation belts. Voyager survived Jupiter. It can survive interstellar space. Temperature is another challenge. The spacecraft has no heaters for most instruments now. Power is too scarce. Some instruments operate at minus 150 degrees Celsius, far below their design specifications. Yet they work. Engineers test components at extreme temperatures on Earth. They want to know when things will fail, but components often exceed their tested limits. A circuit rated for minus 50 might work at minus 100, maybe longer, maybe forever. No one knows until it fails. Voyager's survival defies predictions. Every year, mission planners expect critical failures. Every year, the spacecraft keeps transmitting. The instruments are tougher than anyone imagined. Part of this toughness comes from 1970s engineering philosophy. Over-design everything. Use robust materials. Avoid exotic technologies. If a simple solution works, use it. This conservative approach looks primitive compared to modern spacecraft, but it works. Modern spacecraft use integrated circuits, microprocessors, and complex software. They are more capable, but more fragile. A software bug can disable a mission. Cosmic rays can flip bits in memory, causing unpredictable behavior. Voyager has none of these vulnerabilities. Its technology is too simple to fail in complex ways. The data rate is painfully slow, 160 bits per second. Modern spacecraft transmit at kilobits or megabits per second, but slow transmission is reliable. Less data means fewer errors. Error correction codes can fix most problems. Scientists get complete data sets, just slowly. Voyager's instruments will eventually fail. One by one, they will go dark. But until then, they provide a window into interstellar space. A view no other instrument can match, and every measurement is irreplaceable. The local interstellar cloud is not an isolated structure. It is part of a larger network of clouds, filaments, and bubbles that fill this region of the galaxy. These structures are shaped by ancient supernova explosions, stellar winds from massive stars, and the overall rotation of the galaxy. Around 10 million years ago, multiple massive stars exploded in this region. Each supernova released energy equivalent to 1 billion suns shining for 1 billion years, all in a few seconds. The shock waves from these explosions swept through space, pushing gas outward, creating a cavity. This cavity is called the local bubble. It extends roughly 300 light-years in all directions from our solar system. The interior is hot, around 1 million degrees, and extremely thin. Density is only around 0.005 atoms per cubic centimeter, 100 times thinner than the local interstellar cloud. Our solar system sits near the edge of this bubble, inside the local interstellar cloud, which is a small, cooler, denser cloud within the bubble's interior. Think of it like a fog bank inside a canyon. The canyon is the local bubble. The fog is the local cloud. The cloud moves through the bubble at a different speed than our solar system. We are overtaking the cloud, moving through it at around 43,000 miles per hour relative to the cloud's own motion. In 10 to 20,000 years, we will exit the cloud entirely and enter the hotter, thinner bubble interior. When that happens, the heliosphere will expand dramatically. Without the pressure from the dense cloud pushing inward, the solar wind will inflate the heliosphere to perhaps twice its current size. Cosmic ray levels reaching Earth will drop because the expanded heliosphere provides better shielding. This transition has happened before. Around 10,000 years ago, we entered the local cloud from the opposite side. The heliosphere shrank. Cosmic ray levels increased. Some scientists propose this contributed to climate changes at the end of the last ice age, though evidence is debated. Ice core data from Antarctica shows variations in cosmic ray exposure over hundreds of thousands of years. Beryllium-10, an isotope created when cosmic rays strike the atmosphere, gets trapped in ice. By measuring beryllium-10 levels in ice cores, scientists can reconstruct past cosmic ray levels. The data shows cycles, periods of high cosmic ray exposure lasting thousands of years, followed by periods of low exposure. These cycles correlate roughly with our solar system's motion through the galaxy. As we pass through denser regions, cosmic rays increase. As we pass through emptier regions, they decrease. Voyager's measurements help calibrate these reconstructions. By knowing the current cosmic ray flux in interstellar space, scientists can estimate how much shielding the heliosphere provides under current conditions. Then they can model how shielding changes when we enter different environments. The local cloud is not the only structure nearby. There are other clouds. The G cloud, the fluff cloud, the blue cloud. Each has different properties. Some are denser, some are hotter. Some have stronger magnetic fields. Our path through the galaxy will take us through many of them over the next million years. Each transition will affect Earth, heliosphere size, cosmic ray flux, possibly climate, possibly mutation rates in organisms. The effects are subtle but real. Life on Earth evolved under varying cosmic ray exposure. Our DNA carries mutations caused by cosmic rays over millions of years. Some scientists propose that cosmic ray variations influenced evolutionary history. Periods of high cosmic ray exposure might have increased mutation rates, accelerating evolution. Periods of low exposure might have slowed it. This is speculative, but Voyager's data makes it testable. Understanding our cosmic neighborhood also matters for detecting habitable planets around other stars. When astronomers search for Earth-like worlds, they consider the star's radiation, they consider orbital distance, they consider atmosphere composition, but they often ignore the interstellar environment. A planet in a dense interstellar cloud experiences higher cosmic ray flux. More radiation reaches the surface. Life would need stronger shielding or repair mechanisms. A planet in a thin region experiences less. The environment matters as much as the planet itself. Voyager is mapping our local environment, one data point, one trajectory. but it is the first step toward understanding the larger structure. Future missions might explore in other directions, mapping the full three-dimensional structure of the local bubble and the clouds within it. For now, Voyager flies through the local cloud, measuring, transmitting, revealing the shape of our cosmic neighborhood one measurement at a time. Scientists expected Voyager to detect neutral atoms in interstellar space, atoms that are not ionized: hydrogen, helium, oxygen, nitrogen. These atoms flow through space, unaffected by magnetic fields, because they carry no charge. They simply drift, following their own paths. The heliosphere filters these atoms. As neutral atoms enter from interstellar space, some collide with solar wind particles and become ionized. Once ionized, they become trapped by the solar magnetic field. They cannot penetrate deeper into the heliosphere. This creates a filtering effect. Only the fastest neutral atoms make it through. Voyager detected this filtering while inside the heliosphere. Neutral helium atoms were measured flowing past the spacecraft. Their direction indicated they came from interstellar space. Their speed indicated the temperature of the interstellar medium. By measuring the flow rate and energy distribution, scientists calculated properties of the local cloud. But after crossing the heliopause, Voyager's neutral atom detector stopped functioning. Power limitations forced engineers to shut it down. So direct measurements of neutral atoms in interstellar space are not available from Voyager's current position. However, scientists use other methods to study neutral atoms. Earth-based telescopes can observe how neutral hydrogen absorbs light from distant stars. The absorption creates dark lines in stellar spectra. By measuring these lines, astronomers map hydrogen density and temperature throughout the local interstellar medium. These observations show that hydrogen density in the local cloud is around 0.2 atoms per cubic centimeter, about twice the plasma density Voyager measures. The difference is important. It means half the hydrogen in the local cloud is neutral, half is ionized. This ratio reveals the ionization state of the medium. What ionizes the hydrogen? Ultraviolet light from nearby stars. High-energy photons strike hydrogen atoms, knocking electrons free. The more intense the ultraviolet field, the higher the ionization fraction. The local cloud sits in a region where several hot stars emit strong ultraviolet radiation. This keeps roughly half the hydrogen ionized. But ionization varies with distance from these stars. Closer regions are more ionized. Farther regions are more neutral. Voyager flies through a region where ionization is roughly 50%. Other regions might have different ratios. Neutral atoms also reveal the temperature of the interstellar medium. Temperature determines atom speed. Hotter atoms move faster. Cooler atoms move slower. By measuring the speed distribution of neutral helium atoms entering the heliosphere, scientists calculated that the local cloud has a temperature around 15,000 degrees. This matches plasma temperature measurements from Voyager, confirming that the neutral and ionized components are in thermal equilibrium. They share the same temperature. This suggests the medium is relatively stable, not undergoing violent heating or cooling events. Neutral atoms are important for another reason. They can reach Earth. Ionized particles cannot penetrate the heliosphere easily. They are deflected by magnetic fields. But neutral atoms slip through. They reach the inner solar system. They even reach Earth's atmosphere. Satellites have detected neutral helium atoms from interstellar space entering Earth's atmosphere. These atoms create faint emissions when they collide with atmospheric particles. By observing these emissions, scientists can study the interstellar medium from Earth orbit. No need to send a probe 13 billion miles away. But Voyager's measurements are still essential. They provide ground truth. Remote observations can be ambiguous. Voyager is there, measuring directly. Its data confirms or refutes what telescopes observe. The neutral atom data also reveals something about the heliosphere's shape. The distribution of neutral atoms entering from different directions is not uniform. More enter from the nose, the direction we are moving. Fewer enter from the sides. This asymmetry reflects the heliosphere's shape. The compressed nose allows more atoms through. The stretched sides block more. Scientists model this filtering using computer simulations. They input the observed neutral atom distribution and calculate what heliosphere shape would produce it. The models match Voyager's direct measurements. This validates both the models and the observations. Understanding neutral atom flow matters for future missions. If humanity sends spacecraft to other stars, those spacecraft will travel through regions filled with neutral hydrogen. At high speeds, collisions with hydrogen atoms become significant. A spacecraft traveling at 10% light speed would experience hydrogen impacts like a sandstorm. Shielding is necessary. Voyager travels too slowly for this to be an issue, but it provides baseline measurements of neutral atom density. Future mission planners can use this data to estimate collision rates and design appropriate shielding. The interstellar medium is not empty. Neutral atoms fill it, and Voyager is measuring their presence. Time dilation does not affect Voyager. At 38,000 miles per hour, the spacecraft moves fast by human standards, but slow by relativity standards. Einstein's equations predict time dilation becomes significant only at speeds approaching light speed. Voyager travels at about 0.006% light speed, negligible, but distance itself creates a time delay that matters. Light takes over 21 hours to travel from Voyager to Earth. This means, when mission controllers see data, it is already 21 hours old. Events that happened yesterday just appear now. Voyager exists in our past. This delay complicates operations. If an instrument malfunctions, controllers do not know for 21 hours. If they send a command to fix it, the command takes another 21 hours to arrive. The total response time is 42 hours, almost 2 days. During that time, the problem might worsen or resolve itself. Engineers design command sequences with this delay in mind. They program Voyager to handle problems autonomously when possible. If temperatures drop too low, the spacecraft activates heaters automatically. If power gets too low, it shuts down non-critical systems. Simple logic, no complex decisions, just survival protocols. But sometimes ground intervention is necessary. In 2010, Voyager 2's transmitter suddenly started sending gibberish. Telemetry data became unreadable. Ground controllers panicked. Had the spacecraft lost its mind? After analysis, engineers realized a single bit in computer memory had flipped. Cosmic ray strike. The bit controlled data formatting. With that bit flipped, Voyager sent data in the wrong format. Everything it transmitted looked like noise. Engineers calculated which bit was flipped. They designed a command to flip it back. They transmitted the command and waited. 42 hours later, telemetry returned to normal. Crisis averted. But if they had guessed wrong, or if the problem was more complex, they would have lost the spacecraft. The time delay also affects navigation. Voyager's position is calculated based on signals it sends. By measuring the signal's Doppler shift, ground controllers determine speed. By measuring signal travel time, they calculate distance. But these measurements are always 21 hours old. Voyager's velocity is predictable. Gravity from distant objects barely affects it. The spacecraft coasts through nearly empty space. Predictions are accurate for years into the future. But occasionally, thrusters fire to adjust orientation. These firings slightly change velocity. Ground controllers must recalculate trajectories after each firing. The Deep Space Network tracks Voyager constantly. 3 stations around the world ensure continuous coverage. As Earth rotates, one station loses sight of Voyager below the horizon. Another picks it up. The handoff is seamless. Data flows without interruption. But sometimes problems occur on Earth. Equipment failures, antenna maintenance, power outages, weather interference. When Earth cannot receive Voyager's signal, data is lost forever. Voyager has no tape recorder anymore. It cannot store data for later transmission. If Earth is not listening, the data disappears into space. Engineers schedule maintenance carefully to minimize losses. They coordinate between the three stations. If one goes down, another takes over immediately. But occasionally, gaps occur. A storm hits Canberra, equipment fails in Madrid. Goldstone is already at capacity tracking other missions. For a few hours, Voyager transmits to no one. Those few hours represent months of travel through interstellar space. Measurements lost, cosmic events unobserved. Each gap is painful. Scientists treasure every data point. Losing even a few hours hurts. The delay also creates a psychological distance. Mission scientists watch data from yesterday. They see the heliosphere as it was, not as it is. Voyager could have encountered something remarkable hours ago. They would not know yet. That uncertainty is part of working with deep space missions. Some scientists compare it to looking at stars. The light from stars is years or centuries old. When we observe a star, we see its past. Voyager is similar, just on a smaller scale. 21 hours is nothing compared to years, but the principle is the same. Distance separates us from the present. As Voyager travels farther, the delay increases. Each year adds about 1.5 seconds. By 2030, when Voyager goes silent, the delay will be around 23 hours. Then it will stop mattering. No more data means no more waiting. But for now, the data flows. 21 hours behind reality, a delayed echo from the edge of everything we know. The solar system is not alone. Within a radius of 20 light-years, there are over 100 stars. Some are similar to ours. Some are red dwarfs, cool and dim. Some are binary systems, two stars orbiting each other. Each creates its own heliosphere. Each pushes against the interstellar medium. These heliospheres sometimes interact. When two stars orbit close together, their heliospheres can merge, creating complex structures where three environments meet: two stellar winds and the interstellar medium. Magnetic fields tangle. Plasma flows in unexpected patterns. These interactions are too distant for Voyager to measure, but telescopes observe them around other stars. Our nearest stellar neighbor is the Alpha Centauri system, 4.3 light-years away. It contains three stars. Alpha Centauri A and B orbit each other closely. Proxima Centauri orbits farther out. The system's combined heliospheres likely create a vast region where stellar wind dominates. If Voyager were traveling toward Alpha Centauri, it would take 73,000 years to arrive. But it is not. Voyager 1 heads toward a constellation called Ophiuchus. It will not approach Alpha Centauri at all. The spacecraft's trajectory was determined by its flybys of Jupiter and Saturn. Those gravitational assists flung it in a specific direction. In 40,000 years, Voyager 1 will pass near the star AC plus 79 3888, also called Gliese 445, a red dwarf about 1 light-year away at closest approach, far too distant for gravity to capture the spacecraft. Voyager will drift past silently. 300,000 years from now, Voyager will wander near another star, then another. Over millions of years, it will crisscross the galaxy, pulled by gravity from massive objects but never captured. The spacecraft will remain in the galactic disk, orbiting the galactic center just like our solar system does. But Voyager will not orbit alone. It will share space with billions of other objects, rogue planets ejected from their star systems, brown dwarfs too small to ignite fusion, asteroids scattered by gravitational interactions. All of these wander between the stars, invisible and uncounted. Some estimates suggest there are more rogue planets than stars in the galaxy. Planets form around stars, but gravitational interactions can eject them. A close pass by another planet, a stellar encounter, anything that disrupts the delicate orbital balance. Once ejected, these planets drift forever, frozen and dark. Voyager might pass near a rogue planet someday, within a few light-years maybe, but detecting it is impossible. Rogue planets emit no light. They are colder than interstellar space. Only their gravity reveals them, and Voyager's trajectory would need to pass close for that to matter. The galaxy is also filled with debris, dust grains, molecules, remnants of ancient stars. Voyager collides with this debris constantly. Each collision deposits a tiny amount of energy, slowly eroding the spacecraft's exterior. The golden record might accumulate pits over billions of years. The protective cover might wear thin, but the damage happens slowly. Space is almost empty. Collisions are rare. A dust grain might hit once a month, maybe less. At that rate, significant erosion takes millions of years. The spacecraft will outlast our civilization easily. Interstellar space also contains molecules, water, methane, ammonia, complex organic compounds. These molecules form in gas clouds where stars are born. Some drift into the interstellar medium after stellar winds disperse the clouds. Others form directly in space through slow chemical reactions. Voyager does not carry instruments to detect individual molecules, but Earth-based radio telescopes observe molecular emission lines throughout the galaxy. They map where molecules concentrate. The local interstellar cloud contains traces of organic molecules, though densities are extremely low. These molecules are the building blocks of life. Not life itself, but the raw materials. Amino acids have been found in meteorites, formed by chemical reactions in space. The galaxy is filled with chemistry. Reactions happen slowly in the cold and dark, but they happen. Some scientists propose that life's ingredients are common throughout the universe. If Earth formed from material containing these molecules, then other planets likely did too. The question is not whether the ingredients exist, but whether conditions allow them to assemble into life. Voyager carries no life, no bacteria, no spores. The spacecraft was sterilized before launch, but it carries evidence of life, the golden record, images of humans, animals, plants, sounds of laughter, music, whales, proof that at least one world developed complexity, and it drifts through a galaxy filled with potential. Our galaxy rotates. Everything inside it orbits the galactic center, a supermassive black hole surrounded by billions of stars. Our solar system completes one orbit every 230 million years. Voyager completes the same orbit since it moves with us. But Voyager also moves relative to us. At 38,000 miles per hour compared to our solar system, but much slower compared to the galaxy as a whole. The spacecraft's galactic orbit is nearly identical to Earth's. It will remain in the same region of the galaxy for millions of years. This region is called the Orion Arm, a minor spiral arm of the Milky Way. We orbit at about 26,000 light-years from the galactic center, roughly halfway out. The orbital speed is 500,000 miles per hour, fast enough to cross the width of the United States in 7 seconds. The galactic rotation shapes the interstellar medium. Material closer to the center orbits faster. Material farther out orbits slower. This differential rotation shears the medium, creating structure. Spiral arms form where density waves compress gas. Voids form where rotation stretches it. Our solar system currently sits near the inner edge of the Orion Arm. In a few million years, orbital motion will carry us into the arm's interior. Eventually, we will exit the other side. This cycle repeats every few tens of millions of years as we complete galactic orbits. Each time we pass through a spiral arm, conditions change. Spiral arms contain more stars, more gas, more dust. The interstellar medium is denser there. Star formation happens more frequently. Supernovae explode more often. When our solar system passes through an arm, the heliosphere compresses. Cosmic ray levels increase. Some scientists propose that spiral arm passages trigger extinction events on Earth. The idea is controversial. Fossil records show major extinctions roughly every 30 million years. Spiral arm passages happen on similar timescales. Correlation does not prove causation, but the timing is suggestive. The mechanism would involve increased cosmic rays. More cosmic rays mean more atmospheric ionization. This could affect climate by seeding clouds. It could also increase mutation rates. Higher mutations might stress ecosystems, leading to extinctions. Evidence for this theory is weak. Other factors cause extinctions: asteroid impacts, volcanic eruptions, climate shifts. Teasing out the contribution from cosmic rays is difficult, but Voyager's measurements help. By knowing the baseline cosmic ray flux outside the heliosphere, scientists can model how much flux changes during spiral arm passages. Galactic rotation also affects the local bubble. The bubble is not stationary. It moves with the galactic rotation, but so do we. Relative motion is slow. Over millions of years, our solar system drifts through the bubble's interior, encountering different clouds and voids. The bubble itself evolves. New supernovae occur, adding energy and expanding the interior. Cooler gas from outside drifts inward, refilling the cavity. These processes happen over millions of years. Human timescales are too short to observe changes directly, but models predict them. Voyager will orbit the galaxy for billions of years, long enough to witness many spiral arm passages, long enough to traverse the entire Orion arm multiple times, long enough to see the galaxy change. But Voyager will not witness these changes consciously. It is a machine, no sensors to detect spiral arms, no instruments to measure galactic structure. It will drift blindly, unaware of where it is or where it is going. Yet the spacecraft carries information about where it came from. The Golden Record includes a map, a diagram showing our solar system's location relative to 14 pulsars. Pulsars are neutron stars that emit regular radio pulses. By measuring pulse frequency, someone could calculate when the record was created and triangulate Earth's location. The map assumes pulsars remain stable. Most do. Pulse periods change slowly over millions of years. Some pulsars might shut off or explode, rendering the map useless. But many will persist long enough for the map to work. If an advanced civilization finds Voyager a million years from now, could they use the map to find Earth? Possibly. Pulsars are visible across interstellar distances. Cross-referencing pulse periods with observations would narrow down our location. They could find the right region of the galaxy, the right spiral arm, maybe even the right star. But by then, humanity might be gone. Our star will still shine, but Earth might be lifeless, or our descendants might have spread to other worlds, unrecognizable. The map on Voyager will point to our origin, not our present, and the spacecraft will keep drifting. Radiation is cumulative. Every cosmic ray that strikes Voyager deposits energy. Every solar flare that sweeps past adds more. Over decades, this radiation damages materials at the molecular level. Plastics become brittle. Metals develop defects. Electronics degrade. Voyager was designed to survive Jupiter's radiation belts, the most intense radiation environment in the solar system besides the surface of our star. Jupiter's magnetic field traps charged particles, creating belts similar to Earth's Van Allen belts, but far more intense. Radiation there is 1,000 times stronger than in interstellar space. As Voyager flew past Jupiter, it absorbed a massive dose in just a few hours. Engineers expected some instruments to fail. They built in redundancy, backup systems, shielding around critical components. The spacecraft survived with minor damage. One camera sensor developed a few dead pixels. A memory chip showed errors, but everything else worked. That Jupiter encounter was the most dangerous radiation exposure of the mission. Since then, Voyager has been exposed to lower but constant radiation, cosmic rays, solar particles occasionally reaching beyond the heliosphere. The cumulative dose is now comparable to what it received at Jupiter, just spread over 45 years instead of hours. The difference matters. Rapid radiation damage happens differently than slow damage. Rapid exposure causes immediate failures. Slow exposure allows materials to partially recover between hits. Some materials heal themselves through a process called annealing, where atoms rearrange to fix defects. This makes slow radiation less damaging than the same total dose delivered quickly. Voyager's electronics use simple transistors and resistors. These are more radiation tolerant than modern integrated circuits. A cosmic ray striking a transistor might damage it slightly, but the device keeps working. A cosmic ray striking a microprocessor can flip bits in memory, causing software crashes or data corruption. Voyager has no such vulnerabilities because it has no complex software. The most radiation-sensitive components are the instruments. Some use materials that degrade measurably. The cosmic ray detector's silicon sensors accumulate defects that change their response. Engineers calibrate for this by comparing current readings to past measurements and adjusting. As long as degradation is gradual and predictable, corrections work. But eventually, degradation becomes too severe. Sensors stop responding. Circuits fail open or shorted. When that happens, the instrument dies. Engineers have been shutting down instruments preemptively to save power, but some will fail on their own before power runs out. Voyager's plutonium generators are radiation hard. Plutonium emits alpha particles as it decays. These are stopped by thin shielding, so internal components are protected. External cosmic rays cannot affect the generators significantly. They will keep producing power until the plutonium runs out, regardless of radiation exposure. The spacecraft's transmitter is another critical component. It uses a traveling wave tube amplifier, a vacuum tube device that boosts signal strength. Vacuum tubes are radiation hard because they have no semiconductor junctions to damage. Cosmic rays pass through with minimal effect. This is why Voyager's transmitter still functions perfectly after 45 years. But the transmitter's power supply uses semiconductors. These could fail eventually. If the power supply dies, the transmitter dies with it. The spacecraft would go silent, even if the generators still produced power. Engineers monitor power supply health constantly, watching for signs of degradation. Radiation also affects the spacecraft structure. Aluminum does not degrade from radiation alone. It is too stable, but combined with temperature cycles, radiation can contribute to metal fatigue. Each time Voyager heats and cools, the structure expands and contracts. Microscopic cracks form. Radiation might accelerate crack growth by weakening crystal structure. So far, no structural failures have occurred. The spacecraft is solid, but after another decade or two, fatigue might cause problems. A bracket might break, a boom might bend. These failures would not destroy the spacecraft, but could affect instruments mounted on the damaged structures. The golden record is shielded by its protective aluminum cover. Cosmic rays still penetrate, but most are stopped. The record itself is gold-plated copper. Gold does not tarnish or corrode in space. Radiation might damage the groove structure over billions of years, degrading audio quality. But for the foreseeable future, the record remains playable. Voyager is scarred but functional. Every cosmic ray leaves a mark. Every photon from distant stars deposits energy. The spacecraft accumulates a radiation history, a record of every particle it encountered. If someone retrieved Voyager and analyzed its materials, they could reconstruct decades of radiation exposure. But no one will retrieve it. The spacecraft drifts too far, and the radiation keeps accumulating. The final commands are already written, stored on computers at NASA's Jet Propulsion Laboratory. When power drops too low to operate any instruments, ground controllers will send one last sequence to Voyager. The sequence will shut down everything except the transmitter. No instruments, no heaters, no attitude control, just the transmitter, broadcasting a carrier signal. This signal carries no data, just a tone, a beacon that says, "I am here." Engineers estimate this configuration might last a few extra years. The transmitter uses less power than instruments. With everything else off, the generators might provide enough electricity to keep it alive until around 2038 or 40. But eventually, even the transmitter will fail. Power will drop below the threshold needed to amplify radio waves. the signal will fade. Ground controllers will watch the signal strength decline over weeks or months. Then one day, it will disappear. Voyager will stop transmitting forever. That day is coming. Not this year, not next. But within 15 years, ground controllers know the spacecraft has less time remaining than it has already lived. 45 years of operation, 15 years left. Every transmission is precious. When the signal disappears, controllers will continue listening for weeks. Maybe Voyager is just in a temporary power-saving mode. Maybe a component reset itself. Maybe the signal will return. They will keep the Deep Space Network antennas pointed at Voyager's last known position, waiting. But the signal will not return. After a month of silence, NASA will officially declare the mission ended. Press releases will announce that Voyager has gone silent. News articles will eulogize the spacecraft. Scientists will publish final data analysis. The Mission Control Room, which has operated continuously since 1977, will close. Some engineers have worked on Voyager their entire careers. They started as young scientists in the 1980s, analyzing data from Jupiter and Saturn. They stayed through the Uranus and Neptune flybys. They watched Voyager cross the termination shock, the magnetic highway, the heliopause. They have spent decades with this spacecraft. When it goes silent, they will feel the loss personally, like losing a friend. For them, Voyager is not just a machine, it is a presence, a daily routine. Check the data, send commands, monitor health, troubleshoot problems, year after year, decade after decade, and suddenly it will stop. But the spacecraft will keep flying. No power to transmit does not mean no motion. Voyager will coast through space exactly as it has been, just silently. Its velocity will not change. Its trajectory will not change. It will drift toward that distant star 40,000 years from now, unreachable and unaware. Future civilizations might find it. If humanity survives and develops interstellar travel, we might retrieve Voyager someday. Imagine a mission launched in 2500, capable of reaching Voyager 1's position in a century. By 2600, humans could intercept the spacecraft, bring it home, place it in a museum, or aliens might find it first. The golden record was designed for this possibility. Instructions etched on the cover explain how to play it. Diagrams show the record spinning at a specific speed, a stylus drawing across grooves, the binary encoding of images. Would aliens understand? Maybe, maybe not. The instructions assume certain levels of technology and mathematical knowledge. Any species capable of intercepting Voyager probably has that knowledge. But their senses might differ from ours. What if they do not see light the way we do? What if sound means nothing to them? The record might be incomprehensible, or it might be perfectly clear. A message from a distant world, proof that life exists elsewhere, evidence of intelligence, creativity, and the desire to reach beyond one's own world. Even if they cannot decode the images or understand the music, the record's existence proves something important. We tried, we reached out, we wanted to communicate. The record will outlast everything else on Voyager. When instruments fail, when the transmitter dies, when the structure corrodes over billions of years, the gold-plated disc will endure. Protected by its aluminum cover, drifting through the void, a message from a species that might no longer exist. One day, power will run out, the transmitter will fall silent, and humanity will lose contact with the farthest object we have ever created. That day is not far off now. We should appreciate every transmission while we still can, because soon, Voyager will disappear into the dark, and we will never hear from it again. Scientists built models to predict what Voyager would find. Before the spacecraft even launched, they wrote equations describing the heliosphere. They estimated the heliopause distance. They calculated cosmic ray levels. They simulated plasma interactions. Every model made assumptions. The assumptions seemed reasonable at the time. Space is mostly empty. The solar wind flows outward uniformly. The interstellar medium has average properties. The magnetic field follows simple patterns. These assumptions allowed scientists to build tractable models that computers could solve in reasonable time. But reality defied almost every assumption. The solar wind does not flow uniformly. It varies with solar activity, creating a heliosphere that breathes. The interstellar medium is not average. We happen to be in an unusually thin region. The magnetic field is not simple. It tangles, reconnects, and creates turbulence. Each surprise forced scientists to revise their models, add asymmetry, include time dependence, account for local conditions. The new models are more complex. They require supercomputers to solve, but they match Voyager's data better. Yet even the new models are incomplete. They make simplifying assumptions. They ignore small-scale turbulence. They approximate magnetic reconnection. They extrapolate from limited data. Reality is always messier than models. This is normal in science. Models are tools for understanding, not perfect representations of reality. A map is not the territory. A model is not the phenomenon. Scientists use models to make predictions, test hypotheses, and guide observations. When models fail, they learn. Voyager's data has driven decades of theoretical work, hundreds of scientific papers analyzing the measurements, thousands of simulations trying to reproduce the observations, countless debates about what the data means. Some questions remain unanswered. Why did the magnetic field not rotate at Voyager 1's crossing? Coincidence or something deeper? Why is the boundary so turbulent? Is this normal or specific to our solar system? How much does the heliosphere vary over solar cycles? We have measurements from 2 crossings, but how typical are they? Future missions could answer these questions. An interstellar probe flying in a different direction would provide a third data point. A constellation of probes could map the heliosphere's full structure. Instruments operating over multiple solar cycles could characterize time variations. But these missions are expensive. Billions of dollars, decades of development, political will to sustain them. Voyager benefited from Cold War space race funding. Modern missions face budget constraints and shifting priorities. Scientists make the case. The heliosphere protects Earth. Understanding it matters for predicting cosmic ray exposure, which affects satellites, astronauts, and possibly climate. The knowledge gained benefits humanity. But politicians must balance priorities: healthcare, infrastructure, defense. Space exploration competes with immediate needs. Voyager succeeded partly through luck. It launched during a favorable political era. It benefited from planetary alignment. Its instruments stayed functional far longer than expected. The mission cost $800 million in today's dollars, cheap by modern standards, and it delivered discoveries worth far more. But replicating that success is difficult. Modern missions require more sophisticated instruments, faster data rates, higher power. This increases cost and complexity. Engineers cannot use 1970s technology anymore. They must use modern components, which are less radiation tolerant and more prone to failure. Some scientists propose small, cheap probes, dozens launched in different directions. Accept higher failure rates in exchange for redundancy. If half fail, the other half still provide data. This approach works for near-Earth missions, but becomes problematic for interstellar distances. Communication and tracking consume resources proportional to the number of spacecraft. Others propose a single, well-funded flagship mission. Use the best technology, maximum redundancy, comprehensive instrument suite. This approach maximizes science return per mission but puts all resources into one basket. If it fails, decades of work are lost. Debates continue. Meanwhile, Voyager keeps transmitting. The data continues to surprise. Each measurement refines our understanding. Each anomaly reveals something unexpected. Science is a process. Models evolve. Understanding deepens. Theories get tested. Some survive. Some fail. But knowledge accumulates. What we learn from Voyager will guide future missions, which will learn more, guiding missions after that. This is how humanity explores. Slowly, methodically, one measurement at a time, one spacecraft at a time. Each mission builds on previous ones. Each discovery opens new questions. Voyager is one step in a longer journey, a journey that might take centuries, but it is a crucial step, the first direct measurements of interstellar space, the foundation for everything that comes after, and the spacecraft is still measuring, still transmitting, still teaching us about the universe. For a little while longer, distance distorts perception. From Earth, Voyager appears motionless. Its position changes too slowly to notice. Even over months, the shift is tiny. You could point a telescope at Voyager's location year after year and see no movement. But from Voyager's perspective, Earth races away at 38,000 miles per hour. The spacecraft watches our planet shrink into the distance. First, Earth became invisible, blending with our star's glare. Then Mars disappeared. Jupiter lingered longer, but eventually faded. Saturn became unresolvable. Neptune, the last planet Voyager 2 photographed, is now a faint dot that requires precise pointing to find. The spacecraft sees our solar system the way we see distant stars, points of light. No details, no structure, just brightness, indicating distance and size. Our star is the brightest object in Voyager's sky, but even it appears as a mere point now. The heliosphere's glow, visible in certain wavelengths from inside, has faded. Voyager exists in darkness. Interstellar space is not completely dark. Stars are everywhere. Around 2,000 are visible to the naked eye from Earth. From Voyager's position, the same stars are visible, just in slightly different positions. The constellations we know appear subtly distorted. Lines connecting stars shift by fractions of a degree. A careful observer might notice. The brightest star in Voyager's sky is not the same as from Earth. Parallax shifts change apparent brightness depending on distance. Stars closer to Voyager appear brighter than from our perspective. Stars farther from Voyager appear dimmer. Sirius, the brightest star in Earth's night sky, remains bright from Voyager's position, only 8.6 light-years away. Voyager has moved less than 1% of 1 light-year, so distance to Sirius changed negligibly, but other stars have shifted noticeably. The galactic center is still visible. From Earth, it lies in the direction of Sagittarius. From Voyager, it lies in almost exactly the same direction. 13 billion miles is nothing compared to 26,000 light-years. The spacecraft has barely moved relative to galactic structure. But over millennia, Voyager's sky will change. Stars will shift positions gradually. Some will brighten as Voyager approaches. Others will dim as Voyager recedes. New stars will become visible. Familiar patterns will distort beyond recognition. 40,000 years from now, when Voyager passes near Gliese 445, that star will be the brightest in the spacecraft's sky. For a brief period, measured in centuries, Gliese 445 will dominate. Then Voyager will drift past, and the star will fade. The cosmic microwave background radiation is the same from Voyager's position. This radiation, the afterglow of the Big Bang, fills the universe uniformly. Moving 13 billion miles does not change it. You would need to travel billions of light-years to notice differences. Voyager remains in the same cosmic neighborhood it started in. Dark matter, whatever it is, presumably surrounds Voyager just as it surrounds Earth. We do not detect dark matter directly, but its gravitational effects are everywhere. Galaxies rotate faster than visible matter can explain. Clusters of galaxies stay bound when they should fly apart. Dark matter provides the missing mass, and it exists in the space between stars just as it exists everywhere else. Voyager passes through dark matter constantly. Particles of dark matter, if they are particles, stream through the spacecraft without interaction, trillions per second. But they do not affect ordinary matter measurably. No collisions, no energy transfer, just silent passage. From Voyager's perspective, the universe looks much like it does from Earth. Stars, darkness, distant galaxies too faint to see without telescopes. The spacecraft does not perceive its isolation. It has no sensors for loneliness, no awareness of distance. It simply exists, measuring what surrounds it, transmitting data back to a world it left behind. But humans perceive that isolation. We imagine Voyager alone in the dark, a tiny machine surrounded by infinity. The farther it travels, the more alone it becomes. Distance grows, communication weakens. Eventually, silence. This is the nature of exploration, to leave home, to venture into the unknown, to accept separation. Voyager does this on humanity's behalf. It goes where we cannot. It sees what we cannot see. It endures isolation so we can learn. And from its lonely position, it continues to watch. The stars do not change. The darkness does not end. But somewhere in that darkness, a faint signal reaches Earth. 160 bits per second, a whisper across the void. Still transmitting, still exploring, still alone.